Next we have theorem 16.3 which links product topology with subspace topology. Here we have two topological spaces X and Y, and A is the subspace of X and B is the subspace of Y. Then the product topology on the product A times B is the same as the topology A times B inherits as a subspace of X times Y. So you see two topologies here on the subset A times B. As subspaces of X and Y, A and B themselves are also topological spaces. So you can form their product and give this product the product topology coming from those two topologies, one on A and one on B, which are subspace topologies which are coming from X and Y respectively. So that is one topology, namely the product topology on A times B. But at the same time, because A is a subspace of X and B is a subspace of Y, after all they are subsets. So A times B is a subset of X times Y, but already X times Y has its own product topology from which this subset will inherit a subspace topology. These two topologies on A times B are the same. That is the claim of this theorem. So let's now see the proof. We start the proof by considering a general basis element for the product topology on X times Y. And you already know that such a basis element looks like this. Let U times B be a general basis element for the product topology on X times Y, where U is open in X and V is open in Y. And from a previous result, we also know that if we intersect a general basis element such as this with this subset A times B, then that will be a general basis element for the subspace topology on A times B. Now you look at this identity. That means we are considering this set U times B intersection A times B equals U intersection A times V intersection B. This is a very simple set theoretic identity which you can easily prove. But now you note the form of this set. It's the Cartesian product of U intersection A and V intersection B. Now you look at U intersection A. This is how a general open set in the subspace A looks like, because by the definition of subspace topology, this is how open sets in A look like. Similarly, this is how a general open set in the subspace B looks like. And here we are looking at products of general open sets. So let me now read what I have written here. Since U intersection A and V intersection B are general open sets for the subspace topologies on A and B respectively, so that is why this product is a general basis element for the product topology on A times B. I ran out of space here. So what do we find? We find that a general basis element for the subspace topology on A times B, which it inherits from the original space X times Y, is actually equal to a general basis element for the product topology on A times B. And for the product topology, we use the topologies that A and B individually have, which they themselves inherited by being subspaces of X and Y respectively. So that's it. That's the proof. I mean, if the bases are the same, then the topologies that, there will be only one topology generated by that basis. That topology turns out to be the subspace topology on A times B, that it inherits from X times Y, and it also is equal to the product topology on A times B. And to form that product topology, we use the individual topologies that A and B have, which themselves come as subspace topologies from the original topologies on X and Y respectively. So this is where the proof ends.